Hello, in this lesson, you will build upon the Tic Tac Toe prototype reviewed in the previous lesson. You will be developing and implementing a WinDetector algorithm inside of a specialized WinDetector class. At the end of each turn, your WinDetector class will be able to determine if there are any win conditions in the rows, columns, or diagonals of the game board. Here we're starting with the code of the prototype reviewed in the previous lesson. If you examine the board building code in the game board class, you realize that it simply lays out the game tiles in a square grid. It's not storing those tiles in any sort of data structure, thus it's not able to refer to or analyze the state of the tiles as the game progresses. This state analysis is what is needed in order to perform actions such as detecting win scenarios in the game. So the tic-tac-toe board can naturally be represented by a matrix. For our purposes, we can simply think of a matrix as an array of arrays, which is easy to represent in GDScript. In our case, where we have a 3x3 game board, this is an array of 3 elements, where each element itself is an array of 3 elements, in this case, game tiles. As a first step towards win detection, the build board function is refactored by adding a matrix to store the individual game tiles. In this case, tiles matrix is the array of arrays we just discussed. Now let's dive into developing the win detection algorithm. Breaking down the problem, there are 8 win conditions to check for, 3 row segments, 3 column segments, and 2 diagonal segments. Any given segment can be populated by 3 possible elements on our game board. In this case, there are the string of X, the string of O, and the empty string. With these rules in place, a win condition occurs if we collect a list of unique elements for a given segment, such as a row, and the size of this list is 1. This is a win condition. If the size of these collected unique elements is greater than 1, this is not a win condition. As an example, checking this segment XOX, the set of unique elements would be X and O. The size of this list is 2, so this is not a win condition. In another example, checking this segment, XXX, the set of unique elements would be just X. The size of this list is 1, so this is a win condition. This also works for incomplete segments such as X space X. The set of unique elements would be X space. The size of this list is 2, so this is not a win condition. Additionally, you need to account for the edge case of an empty segment or space space space. The set of unique elements would be space, and the size of this list is 1, but since this is an empty string rather than an X or an O, it should not be a win. In summary, your algorithm needs to be able to iterate over all row segments, column segments, and diagonal segments of a board. For each segment, a win condition review is checking if the returned list of unique elements is of size 1, and that one element is not an empty string. For a clean design, you will create a class that performs just win detection for any given matrix. Add a script for this class in the entities board directory. This class is simply a calculator type class. It has no presence in the scene tree, so it can extend reference versus node. This class will only be functions with no internal state, so we can make its functions static. Starting from basics, implement the logic which can check a list of values for uniqueness. This check is accomplished with 2 functions. First, a function to make a list of values unique. In this case, this is done by leveraging the fact that dictionary keys are naturally unique. So the values are simply fed into a dictionary as keys, then the keys are returned as a list of values. The second function applies our domain logic. It returns false if the size of the unique set is not equal to 1, and true if the size is 1 and the unique element was not an empty string. Now that we can check the uniqueness, we need our check rows, check columns, and check diagonal functions. First, let's look at check rows. This for loop will resolve to 0, 1, 2 for a board with 3 rows. This lets us retrieve each row of the board and send it to the isWinningSequence function. For any given check, if isWinningSequence returns true, that means we sent either XXX or OOO, so we just return the 0th element to the caller, that being X or O. If there are no winning rows, an empty string is returned. Now on to checking columns. This is similar to check rows, but it needs to build a temporary list of each column's values, then send that segment list to the isWinningSequence function to check for a win condition. Lastly, there are 2 diagonals to be checked. A sequence is built for each diagonal segment, and the resulting sequence is sent to the isWinningSequence function, again to be checked for a win condition. Finally, the checks for rows, columns, and diagonals are combined into a single function called checkWin. This enables the caller to call one function to check the entire board for wins. You now have a class that can detect wins in a square matrix containing X's, O's, or empty strings, which is ideal for your Tic Tac Toe game. If you return to the GameBoard class, you recall the board is represented by a matrix, but this is a matrix of game tiles, not the simple strings X, O, and empty space, which the WinDetector class works with. Rather than teaching the WinDetector to deal with tiles, it's easier to teach the GameBoard to dump its state into a matrix of simple strings. The dump state function is added to the GameBoard class. It iterates over the board, inspecting each tile and producing an equivalent matrix of strings, X, O, and empty string. Now the GameBoard can dump its state at any time into a form that works with the WinDetector class. At this point, all that's left is to incorporate wind detection into the game. In this design, at the end of a turn, Tabletop will be asking GameBoard to check for wins, so the getWinner function is added to the GameBoard class. Currently, the end of a turn occurs in the Tabletop class when it reacts to the player-placed game piece on board signal. Here it spawns a new game piece in the holder to start the next turn of gameplay. This is where we can add the check for the win condition by calling the getWinner function, which was just added to the GameBoard class. We rely on the fact that a string such as X or O resolves to true, and an empty string resolves to false. So, if X or O is returned, the winner statement is printed. Now run the game. Line up 3 X's or O's for a win, and you'll see the win statement printed in the debug log. You might be wondering how the representation of the GameBoard is printed to the debug log. Let's take a quick aside and demonstrate that. You can improve print logging by implementing the built-in function toString. In the docs, you see this is inherited from the object class. It is called anytime a string representation is needed of an object, such as in a print statement. In the GameBoard class, the dump state function is leveraged to implement the toString function as seen here. Then in the GameBoard class, you can add a print statement to print the state of the board anytime a game piece is dropped. And this gives you the effect seen in the debug log for gameplay progress. Since toString inherits from object, it's available in all your classes. Thus, you can do the same with other entities to improve the readability of the debug logs. Now you have a generalized win condition checker. The code is isolated in its own class to help keep the code base clean. Thus, in the future, if you have issues with or need to make changes to the win detection algorithm, you have one place to do that work. In this lesson, you added a bit of code for win detection. You've done some ad hoc testing to see that the code was correct. In the next lesson, we'll cover unit testing, which is one way to give you more confidence that the code that's been written is correct. In addition, this gives you a regression net of sorts on the code you've written, so if you make changes in the future, you'll know instantly if those changes have had an effect that has broken the code logic. So thanks again for your time, and we'll see you in the next lesson.